Well, we have just seen that you can compute the feedback matrix K by assigning the poles in closed loop. So maybe we should spend some time on those closed loop pole locations. In theory, the poles can be placed anywhere left of the imaginary axis. So you would be tempted to push them as much to the left as you can, but there are some reasons why you should not do that. A first reason is, of course, the control effort. If you push the open loop poles to the left quite a lot using feedback, well, this will result in a control effort that might become too large. Another problem is also that sometimes in systems the zero is close to a pole, and remember that when you have a zero pole cancellation, well, the system might become uncontrollable. If you have a zero that is close to a pole, it might be controllable, but it will be badly controllable. So moving such a pole away will require a large control effort. You know that in practice there are limits on the control input because, of course, the actuator that you're using, well, has impact because of its size and its cost. Okay, so it's something that you have to design, and you would like to use an actuator that is as small as possible and as cheap as possible. Also, there is a phenomenon that is called actuator saturation. Okay, for instance, the easiest example is a valve. You know that a valve will not open more than 100% and close more than 0%. So that's due to actuator saturation. But every actuator has some form of saturation, and this is really a non-linear effect. If the control effort becomes too big, you might enter in saturation. There are other effects also. If the control effort is too nervous, you might have some limits on the gradient of the input signal, of the actuator signal. And well, if you go above this gradient, you might put stress on the process. So in conclusion, the designer should not attempt to alter the dynamic behavior, the open loop dynamic behavior, more than is really required. Remember that the reason for altering the process behavior, this open loop process behavior, is of course first stability, right? The poles that are to the right have to be moved left of the j omega axis. And the second reason for altering the open loop behavior is performance. We want a fast response, we want fast poles, so a high bandwidth. Okay, but really there are reasons for limiting the bandwidth of the system. As we have seen, it's a good idea to limit the control energy, but it's also a good idea to limit the bandwidth because we know that the noise that is present on all signals is in the high frequency ranges. So if we limit the bandwidth, we'll prevent the system from reacting to noise. Also, well, when we model the system, it's an illusion to think that we have a perfect model of the system. And for instance, for mechanical systems, well, very often we'll have a good model in the low frequency range, but we'll be incapable of capturing high frequency resonances. Okay, so our model might look like this in the frequencies. Okay, let's assume that this is the Bode diagram for the magnitude. It might look like this, but in reality there might be something here happening in the high frequency ranges, in the sense that we were incapable of capturing the resonances. Okay, so there is uncertainty of the high frequency dynamics. So if we use our model here in blue to push the bandwidth of the closed loop system too far, we might excite those high frequency resonances that are unknown. This will lead to degraded performance and could even lead to instability. So we will see three methods for shaping the closed loop dynamic response. The two first methods are such that, well, you first assign closed loop pole locations, right? And this will result in a state feedback matrix K. The third method is different in the sense that here you will have a cost function, right, that you will have to, well, select, design, and optimizing this cost function will result in the state feedback matrix. The first method is the dominant second order pole method, and the idea is that we assign the closed loop poles as follows. So here you have the S plane, so real part of S and imaginary part of S. Of course, we often have a higher order system, so there will be more than two poles to assign, but what we'll do is assign a pair of dominant second order poles as shown here in blue, right? And we'll see how we can assign these pair of dominant poles and what their effect is on rise time, settling time, and overshoot. And what we mean by dominant second order poles is that the other poles that will be drawn here in green are sufficiently to the left, they are sufficiently fast with respect to the dominant second order poles that their effect is neglectable, and that the overall closed loop response will look like a response of a second order type with complex poles, right? We will see also that there is the influence of the zeros. Remember that with state feedback you cannot affect the zeros, but we will see that as long as the zeros are located between quotes far away from the dominant poles, the effect is rather small. The second method is the Butterworth pole configuration method. We have seen previously that if you want to assign a pole far from the origin, this will require a lot of control energy, and if you assign a pole close to the origin, this will result in a slow response. So the idea behind this Butterworth configuration method is to put all the poles at the same distance of the origin, okay, and this is therefore a very systematic method. Well, the third method is optimal control design, and the idea that is that a cost, which is the integral from 0 to infinity x transpose qx plus u transpose r u dt, is minimized. And in here you have a compromise between two things. Well, having the state go to 0 as close as possible, and the other one is really limiting the control energy. In this slide we review the second order system with complex conjugate poles. It has transfer function that is given over here, and this transfer function should look familiar because it's a review of what you've seen in the course of my colleague David Rouchard in his course of fundamental control theory. Omega n here is the undamped natural frequency. Zeta here is the damping ratio. It's a number in between 0 and 1, and you can see that the damping really is affecting what is called the damped frequency. If you complete the squares on this denominator, if you complete the squares on these two first terms, well, you construct a first square over here, s plus zeta omega n, and this will produce s square, this one, plus 2 zeta omega n s, and then you'll have also zeta square omega n square. Okay, and this zeta square minus omega n square you have to subtract, and so you end up with the second term over here. This is to show you that it's rather easy to obtain the poles of the system. Okay, and you could do this as an exercise. It's not that difficult. You can also compute the step response, and it is given over here. Well, as you can see, the real part of the pole is minus zeta omega n, and we'll call it minus sigma, and the imaginary part is really the damped frequency omega d. Well, if you use this expression that we obtained from the step response and you use it, for instance, in MATLAB Simulink, you can obtain a typical step response of this second order system with complex poles, and it's given here in green, and we'll use it to define a number of quantities that will be important in this course. The first one is TR, and TR stands for rise time. It's the time that is needed to go from 10% of the final response to 90% of the final response. TS is the settling time. It's the time that is needed for the response, the step response, to settle in a band of plus minus 1% of the final response. We'll use also sometimes the peak time, and this is the time for the first peak, and then we'll have also the overshoot, and the overshoot is expressed in percent of the final response. Okay, and this final response is given over here, right? And in the next slides we'll link these quantities with the important parameters, which are the natural frequency and the damping ratio zeta. Well, this is the dominant second order pole configuration. You see here that the pair of complex conjugate poles are over here, right? So the real part is sigma, it's omega n zeta. This is what we had obtained previously, and the imaginary part is the damped frequency, which is the natural frequency times the square root of 1 minus zeta square. You can also see that this distance over here is omega n, the natural frequency, and that the damping ratio zeta is related to this angle over here by the relation theta is the arc sine of zeta. You say that this is indeed consistent, because if you're working in this right angled triangle, you see that this distance here, sigma, is indeed omega n times the sine of theta, okay, the sine of the arc sine of zeta, so you'll have omega n times zeta. So everything is consistent in here. You've seen in the course of my colleague that the rise time, overshoot, and settling time are related to the quantities omega n and zeta. The rise time is 1.8 over omega n. So what is important here is that this rise time is in 1 over omega n. So if you want a rise time that is small, well, you should go in this direction over here, right? So this is TR that is becoming smaller. If you look at the overshoot, the expression is given over here, and you can see that when theta is moving in this direction over here, so if you push this down, right, then zeta will become closer and closer to 1, and you will see that if you would put a zeta here that is closer and closer to 1, because of this 1 minus zeta square, you'll have the exponential of something minus something that is large, so this will go to an overshoot of 0. So if you want to decrease the overshoot, you should push over here as I have shown. The settling time, right, this is really the time ts that is needed in such a in order to have e to the minus sigma ts is equal to 0.01. This is this 1% band around the final response, right? If you compute this exactly, this is what you obtained, but you will use this approximation that was already used in previous courses. So the settling time is 5 over sigma, where sigma is the real part of the poles. So if you want to decrease the settling time, what you should do is, well, increase the real part. So you should go this way, and this will decrease ts, right? And this would decrease the overshoot. Well, we have just seen that the rise time is, well, influenced by omega n, the natural frequency, and if you push this way, well, you will decrease the rise time. The overshoot is related to this angle theta, which is indirectly related to the damping ratio. So if you push this way, the overshoot will decrease. And finally, the settling time, well, is related to the real part of the pole, sigma, which is equal to omega n zeta. So if you push this way, you will decrease the settling time. As you know, good performance is a mix between an appropriate rise time, an appropriate overshoot, and an appropriate settling time. So really, when you have good performance, the appropriate pole region for good performance will look like the intersection of those three regions, as is shown over here. So here's a pragmatic approach for the assignment of the dominant second order poles. Well, first of all, stable modes that are fast and well damped should be left untouched, so there is no reason why you should move these. Unstable poles, which are to the right of the imaginary axis, should be, of course, brought to the left of the imaginary axis for stability, right? So the easiest thing is to replace them by their symmetric counterparts with respect to the j omega axis, and then to check the three performance indicators related to rise time, overshoot, and settling time. The performance constraints on the settling time will impose a minus sigma parallel on the dominant second order poles that you have to assign. So slow real stable poles situated to the right of this minus sigma parallel should be brought back on this line to accelerate the closed loop response. Insufficiently damped complex poles should be brought back on the specified damping lines that are consistent with your performance specifications. Well, what you have seen previously is of course valid for the simple second order system, which means that you would have only two dominant poles to place, and we forget about additional poles and additional zeros. So in reality things become a little bit more complicated, but what we have seen here can still be used as a guideline. So if you have a certain design, right, and you see that the rise time is too slow, what you should do is increase the natural frequency of the dominant poles. If the transition has too much overshoot, and when you do a step response, then you need to increase the damping of your dominant second order poles. And if the transition persists too long, in the sense that the settling time is too long, well, then the poles need to be moved to the left in the complex plane. Nevertheless, it is interesting to study the effects of an additional zero or pole, and this is what we'll do in the next slides. So let us have a look to the presence of an additional zero. So we'll consider a transfer function with the same denominator, and again we can do the completion of the squares. Sigma here is omega n zeta, and omega d is the natural frequency times the square root of minus zeta squared. Okay, so if this term disappears, we have the transfer function that we have considered before, but we have added this term over here. So this means that we have now still a unit steady state gain, right? The steady state gain can be obtained by considering S is equal to 0, right? If you consider S is equal to 0, it's easiest to see it over here. We see that we still have a unit steady state gain, and we have the presence now of this 0 in minus alpha sigma. So you see that when alpha is large in modulus, okay, you can see it over here, the presence of the 0 will have very little effect on the response, and this 0 will be very far from the two complex conjugate poles. If alpha is approximately 1, then the value of the 0 will be close to the real part of the poles, and a substantial effect can be expected, as you can see over here. And when the value of alpha decreases to 0, well, the influence of the 0 will further increase, as you can see over here. So what we'll do in the next two slides is use the expression of the step response to look at the influence of alpha. We'll consider two cases: alpha positive, right, and then alpha negative. And we will see that this corresponds to a system with an inverse response. We have seen this before, or you have seen this before in other courses. A good example is the lead lag system, and its transfer function is over here. If you look at the step response, it will look like this, at least if the lead is negative. Okay, so you could compute the response of the step response, but what we'll do is use the initial value theorem to compute y of 0 in the case of a step response. We'll have to take the limit when s tends to infinity of s times the response in the case of a step response. So we'll have k t lead s plus 1, t lag s plus 1 times 1 over s. The 1 over s and the s will cancel out, and this will lead to k t lead over t lag. Obviously t lag will be positive, otherwise you would have a lead lag system that is unstable, and well, it would make no sense to look at the step response. So t lag is positive, but you see here that when t lead is negative, indeed you have this inverse initial response. Okay, so at time t0 you will have something that will go down, right, before of course going to the value of k, because in steady state the gain will indeed be k over here. So here we have the step responses of the systems with a 0 in, and so the 0 is in minus alpha sigma, and you see here in blue, well, we have the response where alpha tends to 0. So basically this is the response, the step response of the transfer function without the 0. So it's this one over here. Okay, and as you can see, when alpha is large, for instance when alpha is equal to 10, there is very little influence in the step response, and well, the influence becomes larger and larger when alpha decreases, and when alpha is equal to 1, you're really in a situation where this is the complex plane, right, real part of S, imaginary part of S. So you would have your poles, for instance, over here, and the 0 would be right here. Okay, and you can see that if this is the case, well, the influence of the 0 will be quite substantial. So previously we have considered the case where alpha is positive. By the way, we have normalized everything in such a way that you can draw step responses independently of the natural frequency. In this case, we'll take alpha negative. The 0 is in minus alpha sigma. So this means that this 0 is to the right of the imaginary axis, and this is explaining why we see these inverse responses, these inverse step responses. Again, when alpha in modulus is large, well, the presence of the 0 is hardly felt, and when alpha is tending to minus infinity, well, you have the step response of the original transfer function without the 0. So this is this transfer function here. So when the modulus is decreasing, alpha is still negative, but its modulus is decreasing, you see that the influence of the 0 is felt more and more, and here you see this in this, well, inverse responses. The situation in green comes from the following case. So here you have the complex plane that is drawn, the real part of S, and here the imaginary part of S. So we'll assume as before that the poles are located over here, the complex poles. And the situation that corresponds to the green line is that, well, you have here the real part, sigma. You draw it over here, and this leads to a 0 over here, right? So the situation that is drawn here corresponds to this case over here. In the present study, we have taken zeta, the damping ratio, is equal to 0.5, and we have looked at, well, different cases of alpha to study the presence of an additional zero. And as you can see, there is really a large influence on the overshoot. Remember that alpha is equal to infinity, corresponds to the response where there is no zero, and we know that for zeta is equal to 0.5, the step response in this case will give approximately an overshoot of around 16%. So what you see here is the influence of the additional zero on the overshoot. Okay, and we consider three situations: zeta 0.3, zeta 0.5, and zeta 0.7 with the respective colors. You remember that when alpha in modulus is sufficiently high, and let's say that alpha is either smaller than -4 or higher than 4, the influence of the zero is hardly felt, and indeed what you obtain, right, is the percentage overshoot that you would expect with the original transfer function without the zero. So with a zeta that is 0.7, you would expect something around 5%. This is indeed correct. 1, 2, 3, 4, 5. So this is approximately 5%. Zeta is 0.5. Well, we have seen this is approximately 16%. And with a zeta is equal to 0.3, well, this is approximately 35% overshoot. Okay, well, of course, when alpha is decreasing in modulus, so if you go in this direction or in this direction, you can see that the effect of the zero becomes larger and larger, and of course it becomes, well, dramatic when alpha is close to zero. So we'll now consider the case of an additional pole, and again we'll introduce the pole in such a fashion that the steady state gain is preserved. We still have a unit steady state gain, and because this is a sigma over here, and we see here that the pole is in minus alpha sigma. Of course, here we only consider alpha positive because we only consider transfer functions that are stable. You can see that when alpha is going to be very large, this pole is going to be so fast that there will be hardly any effect on the step response. If alpha is close to 1, then the additional pole will be close to the real part of the complex poles. Okay, we'll have a situation that will look like this. So real part of S, imaginary part of S, the complex conjugated dominant poles, well, they will not be dominant anymore in this case, are located over here, and the additional pole is located over here. It's a real pole, and in this case, well, you can expect a substantial influence, and in this case, well, the major effect will be, of course, that you will slow down the system, and this will increase the rise time. So this is what you see here in this step response plot, where alpha gives you, well, the step response with different poles. Remember that when alpha is tending to infinity, well, this third pole is so far that you can neglect it. So the response here in blue is the one that you have with the original transfer function that is the following one. And as you can see, if alpha is large, right, well, the effect on the step response is rather small. And then when the modulus starts to decrease, the effect on the response becomes larger. As you can see here, indeed, the system here in green that corresponds to the situation that I have depicted in the previous slide, well, is such that you have a much slower response. As we have said before, the rise time has increased quite dramatically. So here's a summary on performance and on how you can shape the dynamic response in the case of dominant second order poles. Well, for a second order system with no finite zeros, you can use the following rules of thumb. The rise time is approximately given by this expression here, and it's mainly influenced by the natural frequency. Here we have a series of overshoots that correspond, of course, to values of the damping ratio zeta, and the settling time Ts is approximately given by this equation, 5 over the real part of the dominant poles. Associated with this, you should have a look also at the region of good performance. Well, obviously in most designs you have the presence of a zero, or more zeros, a pole or more poles, and a zero either in the left half plane or in the right half plane will typically increase the overshoot if the zero is within a factor 4 of the real part of the complex poles. An additional pole in the left half plane will increase the rise time significantly if this pole is within a factor 4 of the real part of the complex pole. So here we have a case where you have so-called good performance. You have located the dominant second order poles as follows, and the other poles are sufficiently to the left. Well, the presence of the zeros is a bit different because this is not something that you can affect using state feedback. So you'll have to live with the presence of the zeros, and if the zeros are sufficiently far away from the dominant poles, either to the left of the imaginary axis or to the right of the imaginary axis, well, you will not have a lot of influence on the closed loop response you're hoping for in your design. You will see that the result of a pole placement will not always be as expected if you implement on the actual system, and there are several reasons for that. The first one is, of course, model mismatch. The model that you're using to design your state feedback is, of course, never a perfect representation of the actual system. For instance, very often the process is a non-linear system and your state space controller is based on a linearized model that at best can represent the system around some operating point. Remember also that often you have the presence of zeros, and they can have a substantial effect on the behavior that you're expecting through your dominant second order pole method. And this is especially true for non-minimum phase zeros, so zeros that are to the right of the imaginary axis. So if you work, for instance, with a inverted pendulum type system, you can expect those kind of zeros. A very important comment is related to this second item over here. When you're going to test a design in simulation, please test it always on the non-linear model, right? I very often see students that test the design on the linear model, but you know that the non-linear model will be closest to the actual system. So you should check all your designs, controller design, observers designs, on the non-linear model so that you can see the effects of the non-linearities. Okay, remember that you've based your design on linearization, and you going to take also into account the effects, for instance, of saturation. Well, in the control lab that is associated to this course, you will have to work on a given system, but I will most probably not give you any specifications in terms of rise time, settling time, and overshoot. This is your job. You should try several designs and see how far you can take it. The idea is that you kind of show me that you've really understood the influence of the choice of the poles on the shaping of the dynamic response. There are many pole configurations that you could test. So obviously you could test the dominant, and this is each time the real part of S, imaginary part of S, right? You could use the dominant second order pole method with dominant complex conjugate poles as shown over here, right, with other poles that are sufficiently far. What you could do also is, for instance, work with one dominant real pole and put the other poles sufficiently far, right? Or you could work with two dominant real poles that are close to one another and you put the other ones sufficiently far. There are plenty of ways to obtain a good design, so be creative, put an element of originality in your work. And the next thing that you could use is also this Butterworth configuration that we're going to see right now. The idea behind the Butterworth pole configuration is that it is imprudent to move poles further away than necessary, and that it is inefficient to put them at different distances from the origin. So the idea is to put them all at the same distance from the origin in the left half plane. Remember that the rise time Tr is related to the natural frequency through this equation, so it's approximative 1.8 over omega n, and this distance to the origin is exactly this natural frequency. So the criticism is then, well, we look to the rise time, but what about the other performance criteria such as overshoot and settling time? Also, it is not clear what the influence is on the control energy and if this method is going to produce controls that are not too nervous. Well, let us look at an example. The Butterworth pole configuration is obtained using this equation here, where S is really j omega and k is the number of poles assigned in the left half plane. If you look at this equation, it's of dimension, well, of power 2k, so there will be 2k roots, but only k of them will be in the left half plane, and these are the ones that we have to select. So let's have a look at a case where we want to place two poles in the left half plane, and we'll have k is equal to 2, and the equation will be j omega divided by omega n to the power 4 is equal to minus 1 to the power 3, so minus 1. J to the power 4 is 1, so we have the relation omega 4 is equal to minus omega n to the power 4. So if we take the square root, we have minus 1 is e to the j pi. So we'll have omega squared is equal to plus minus eg pi over 2 omega n squared. And if we take another root, we'll have omega is equal to plus minus eg plus minus p over 4 now omega n. So indeed there are 4 roots. If we have a look, so this is omega n over here, and the roots are given here, 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 and here. As you can see, there are 4 roots. 2 of them are in the left half plane, and we'll select the ones that are in the left half plane. In this slide we show the Butterworth pole configuration for k is equal to 3 and k is equal to 5. So in both cases k is uneven, and you see that when k is uneven you have the presence of one real pole. The other poles are complex conjugate. If you take an even k, then all poles are complex conjugate. The angle that you have between the poles is 2 pi divided by 2k, which is pi over k, and in this case here it corresponds to an angle of pi over 3, so 60 degrees.